Thanks for informing this. I thought somebody's already started recording. Anyways, I'll start recording from next. Okay. So as I mentioned, uh, this gate level abstraction from this transistor is nothing but representing a group of transistor using a gate, higher level gate. Also, I am actually ignoring their actual positions, actual interconnection path, all those things. I just represent them as just a graph. In my graph, a node is but a AND gate or a OR gate is nothing but a just node in the graph, right? And their connections is nothing but the edge. So this is the abstraction I have done. And EDA tool will help me to the reverse thing. That once I give this gate level design, it can give me the transistor level design automatically. It can do certain kind of optimizations there. I'll come into those in detail. And then it will help me to place all those gate transistor physically in a given area. Okay. So that's something we'll do this. This is what is called physical synthesis. So from transistor, I do abstraction of gate level. So still this is 1 million number of gate, which is something is huge, and developing a circuit in gate level in context of a billion transistor things is impossible. So then the next abstraction comes, and the next abstraction is register transfer level design. Okay. So in the register transfer level design, what happens? So now you think about your digital design class that you have a full adder, right? So a full adder is, you can always represent them as a gate level, but in higher level you can just think about a node which is just doing a plus b, right? So in the register transfer level, I abstract out that things. I'm not going to represent a adder using a gate level circuit, a multiplier using a gate level circuit. What I'm going to do, I'm going to just write a plus b. Suppose I'm doing a plus b, I'm just going to write, say, out equal to a plus b. A, B, and out, those are all registers, right? So I'm extracting out all the detailed representation of those adder, multiplier, and other things, and I'm representing the whole circuit in terms of transfer of register values, right? That's why it is register transfer level. So I'm just going to write A equal to B plus C equal to B minus D, and so on, right? So this is what is called register transfer level. But still, at this level, you have clock, because you have registers, memories, and all. You have all this clock, reset, set, all those things, and you have up all those details, because otherwise things won't work, right? So, but I make a 10x jump, right? I don't have to represent my adder by a get level design. I am going to represent that as a plus b in that thing. So this is what is called register transfer level, and this is what is the de facto standard in the this design houses like Intel, Apple, Samsung, and many this NVIDIA and all. So usually design start from this register transfer level, right? People always think about any hardware, it's RTL, right? RTL, and it can be represented in a Verilog language like Verilog VSTL, but it's level called RTL. So this is what is called register transfer, the another level of abstraction. Okay. So once you do this abstraction, again you need a tool, right? The tool will take a register transfer level design and then automatically convert into a gate level design, because whenever I found a plus b, I know this is, it can be a full adder, it can be a carry look ahead adder, it can be carry sensitive adder. Based on your target clock and other parameters, I'm going to choose the appropriate gate level representation of that adder, right? For a multiplier, you have boost multiplier, you have many other multipliers, right? So you can actually the best one based on your target optimization goal, right? So my, this is called logic synthesis. From register transfer level, I have EDA tools, softwares, which will convert that particular register transfer level design into a gate level design by converting those abstraction into gate level representations. Again, it do lot of optimization. Again, those optimization you will not understand at this moment, but it does lot of optimization as well. Okay. So this is the overall flow of the EDA softwares or the EDA tool chain, which is getting used in the industry. And what next, right? That is what is our course. That is that we need more abstraction, right? So that is what next in this particular slide. That even RTL, you think about a billion level billion gate transistor, it may be around 10 million line of code in RTL also, which and thinking about this design where you have to see that their clock level cycle accurate performance, it's not so easy. Cycle accurate in the sense every clock the design is actually performing correctly, right? So cycle accurate performance evaluation even with the 10 million 20 million line of code in RTL level is become too much, right? So we need more abstraction, right? And that is where our course come into play. I'm going to make another level of jump from RTL to C, or higher level of C is just a representation here, representative name, but it's a more higher level of behavior where I do not have to bother about clock, reset, memory set, all those synchronization, asynchronous designs, frequency, clock, nothing we don't have to bother. I just want to bother about the functionality of the or the specification of the uh, your design, right?
Sir,
Then this, yes, hello,
sir, are you on the page number 9?
yes, I'm in the page number.
Okay, sir. I
So
think the screen is stopped there.
no, I am there only. So I'll go to the next slide. Okay. So so this is where this C-based VLSI design come into picture, and this C to RTL conversion is called high-level synthesis. Okay. So we want to do high-level synthesis to convert a C code into a register transfer level design. So this is the EDA flow, and that is the primary focus of this course. Okay. So as I mentioned, this is the same flow that from the layout, I go higher level up, and finally I will come to a specification which is just written as a CDFG or a C code, right? High level behavior, and then automatically my software will give me the layout. Okay. So the advantage of this automation is something very much clear, that it's a shorter design cycle. Developing a code with 9 billion, 10 billion transistor is not possible, but probably a code of 10,000 line of C code is much. When developing a code of ASA or 10,000 line of C code, which is much simpler or less time compared to 10 billion transistor level circuit design, right? So that is what is the primary advantage of this design automation, the shorter design cycle. Second advantage is the design exploration, which is another biggest advantage of this high level synthesis tool. Is suppose I have given a specification, right? So I want to develop a circuit which is as fast as possible, right? So I don't care about the area, but I want to run this in 200 megahertz clock, say. So that may be one objective. And now from the same specification, I want to design another circuit, say where I am more focused about the area. Area should not go beyond say 1 million number of transistors. So then I don't care about the clock. I may be able to run the circuit in 50 megahertz, and that I'm okay with that. But my area. Similarly, suppose your target may be power, that I want to use as less power as possible. I want to make a low power design from this, right? So for all these things, if you want to develop a gate level design or a RTL level design, you have to develop them from scratch. There is no interrelation between them. So you have to have a different design for different goals. But with high level synthesis, I have a same C code, and I can utilize the software high level synthesis tool, which with the target objective, it will design an RTL automatically from a given same specification. So that means explore the different kind of design from the same specification within seconds, within minutes. I can get many kind of RTL design or the hardware design from the same specification. Whereas if you want to do the same thing in RTL, it will take years, right? So that's the difference. So from within minutes to years, the kind of advantage you are going to get here. And obviously, when you develop a circuit with 10 million line of code versus 10,000 line of code, the human error will be less, right? When you write a big code, always you make some mistakes. So obviously, if the code length is less, the probability of error is also less. And advantage like verification is easy, and then you can apply different kind of optimizations. Those will come into later. Okay. So next slide. So this is the overall EDA flow as I mentioned. So we have the layout. From that we can extract a transistor level behavior. From transistor level behavior, uh, I will I will go to this gate level design. So just a minute. So from this layout, I'll go to this transistor. From transistor level, I'll make abstract level of gate level design. Gate level, I'll make a abstraction to the RTL, and from RTL, I'll go to the higher level specification, which is our C code. Okay. So this is the flow. I'll talk about this in more detail in subsequent classes. So this is the overall flow: high level synthesis, logic synthesis, physical synthesis. Then you do the actual, then package and test the design. Okay. And I mentioned that your optimization goal can be different: speed, power, reliability, area, many things can be there. So based on your objective, you have to develop your tool which can actually meet this particular objective. Okay. Any questions so far? Okay. So so primary focus of this course is C2 RTL design. So if you have a, so basic idea is that I'll give a C code like this, and then so I'll give you a C code like this, and then my software or the EDA tool automatically convert this into a register transfer level description, which will consist of a data path and a controller. Again, we'll come back on to know all things later. But this is what is the tool all about. This is what the C-based VLSI is all about. Okay, and this is where I'm going to uh, uh, spend most of the course, most of the time in the course in this particular part. Okay, the C code into RTL and equivalent RTL. So it's basically high level synthesis is also not something is lagging behind in the industry. If you look into this, all these big design houses like Synopsys, they have a high level synthesis software. Xilinx has a Vivado. Intel has OpenCL. Mentor Graphics has Calypso, and then Cadence has Forte. So all these big EDA software companies already have a commercial high level synthesis tool available. Okay, so it's basically getting popular, and uh, so we are going to use the tool developed of Xilinx called Vivado high level synthesis tool for the project purpose in this course. I think this is the first part, okay, of this in today's discussion, that we need to automate the whole process. There is no question about that. We need to automate the whole process. And and next part is that what is the general purpose? Why need this kind of specialized hardware, right? So we are thinking about always a specialized hardware. Why we can't this general purpose processor like our desktop servers own work is not sufficient, right? That's something is another part. Why I'm going to spend this much of effort in
Hello,
this
sir.
course? Or, yeah,
Hello, sir.
yeah, yeah. Tell me.
Yes, sir. Sir, as you told, like we need to convert from a C-based code to a design part. So, sir, actually, are in this course are we trying to design a tool or somewhat like that, which converts a C code into a design?
We'll try to go the inside of those tools. It is not possible to develop the whole software in the course, but
Okay.
how that tool works in general, in more detail. Okay.
Okay. Okay, sir.
Huh. Understood. Right.
Yes, sir.
Okay. Okay, so let me just move to the next part of the course, that why the general purpose processors are not sufficient, and we all people are looking for specialized hardware. Okay, so so just to give you the idea, the primary idea is that this general purpose processors are inefficient because first of all they are very slow, and they take consume lot of power, lot of energy. Okay, that is the overall in short answer. I'll give you more this. So if you just think about that, our this initial figure that I have shown you, that the chip size is shrinking, right? But the number of transistor getting increased. Right? So how then I can fit more transistor in a small space, right? So how we can do that? Only by reducing the size of. There is no other alternative, right? I want to make a tiny mobile that will fit into my pocket. I want to have a very lightweight laptop which I can carry with my cabin luggage. So, and which actually have now more number of transistors, right? Billion transistors. The only option is that you scale down the size of the transistor. That is, this is was developed. I mean, there was a forecast by Gordon Moore, I think in around 1970 of Intel. He says that in every 18 months, the size of the transistor will become basically, it will say like this, that the number of double, right? It was something like this. So and that means, but the size, if you think about the size of that particular area of that chip remains same, it means the size of the transistor has been, has to be reduced, right? And if you, this particular diagram is showing that in 2001 the 180 nanometer, so that means in the transistor between the gate and drain, that the distance is 180 nanometer, and then it is actually shrinking because you want to put more transistor into circuits, right? So it come to 180, 130, 90 nanometer, 65 nanometer, so on, and then around it is 14 nanometer, right? And then it is not shrinking further because you cannot make it, and after certain time the electric functionality of the transistor won't work, right? So I think by after 7 nanometer we cannot reduce it further. So I think 7 nanometer chips are not still available. I think 10 is already there in the market, 10 nanometer. But in couple of years we will reach the end of Moore's law. It means we cannot reduce the transistor size further, right? Because otherwise the whole electric functionality of the transistor will work. Then what is the solution? So I cannot make my transistor smaller, but I need more efficiency. I have machine learning algorithms, I have other things. So how I can do that, right? So then uh, it comes this the concept of this multi-core, right? So it's already very popular. So if you look into this particular chart, it's very a lot of things are mapped into a single chart here. You can see here that uh, so basically this is from 1975 to 2015. So the number of transistors is getting increased. Now in 2010 the number of transistors is 1 billion, right? 10 to the power 6. So the number of transistor getting increased, and initially till 2005 or 2004 we are used to have a single processor, right? We do not have a multi core. But the power was growing very fast, right? So it is growing very fast, and beyond a certain limit, when it reaches 100 watt, you cannot go beyond a certain limit, right? So you have to do something, and then the concept of multi-core design comes, right? Instead of making one particular processor very efficient or very complex, let's take multiple processors which is less powerful and use them. So by 2000 we have 64 processors here, right? So we are putting more number of less powerful processors into a in a particular design, instead of making one particular processor too powerful, right? That was the design. I mean, change in the design paradigm, that from a single processor making it more complex processors where each processor is taking less power and they are less powerful, right? So, and if you see here from that, so after a certain period of time, the sequential processor performance does not go that fast. Rather, to match the performance, the parallel processor come into, right? So here is that even if you put multiple processors, the total power is more, right? Although each of the processor core is taking less power, but in union of the whole processors will take a lot of power, right? So even the paradigm shift from a single processor to multi-core or multi-processor, things won't give you the final solution, right? And the simple reason is that the total power cannot go beyond certain limit. And this is what another interesting the slide. You can see the modern day things are taking a lot of power hungry things, right? So one our laptop is taking some 50 watt per chip, servers are taking 100 watt and so on. Even a mobile take 1 watt per chip, right? And now we have multiple processors are there. So obviously, this particular game, that to keep the power lows, you have, so power is basically energy per second. So you can actually rewrite this sentence like the energy per operations into operation per second. So if you reduce the energy per operations or you increase the operation to be executed per second, then your total power will reduce, right? But every time, so there is a limit of that. So and we reach kind of the end of Moore's law and all. So all these things got come to a limitation. So even this multi-core won't solve the actual purpose. Then what is the solution? We need specialization, right? We need specialization. So basically, there is a very nice diagram here. Is that even the human civilization advancement comes specialization, right? We have doctors, we have engineer. In the engineer, we have a mechanical engineer, electronic engineer, computer science engineer. So we have a very specialized domain where somebody is very specialized in a particular area, and he does the wonder, right? So this is the basic things. That is how the our civilization advances, and the same this VLSI design also following the same path, or the computer is also following the same path. Instead of having a general purpose processor, you make a application specific processor or the hardware accelerator, right? So what does that mean? If you see, this is I think S10 or something, that architecture. So you have, see how many components are there. We have this camera. There is a particular hardware accelerator that will actually process the camera images and all those things. We have JPEG encoder. We have audio, some that will make sure audio noise and all those. You have so many things, right? I mean, I am not enumerating all, but you can understand. So we have a general core processor here. He's sitting there, but there are maybe 50 different other hardware accelerator or the specialized hardware. So general purpose processor is something which can do anything. It can do all. A camera software that is actually processing this camera photo, that can only do that things. It's a specialized hardware accelerator. But that is how this particular, nowadays we see this wonder in this electronic design, that we have a hardware accelerator or a specific application specific design that will is a tiny, so small. It is not developed for doing everything. It will do only one thing. So it need less power. It is it is faster because it is only designed for a particular job, and it's taking less area. So everything is solved with this, right? So that is where this specialized design or specialized hardware into picture. So if you look into this, the design paradigm, as I mentioned, the general purpose processor or the microprocessors are the best thing to do, right? So where you can actually run, so for example, in our computer, we can play a video, we can run a C code, we can watch a movie, we can run internet, we can run anything, right, in a processor. More flexible. But if you go towards this, so then come DSP and then FPGA, so the efficiency goes up when you go this direction, but flexibility is less, right? If you go to ASIC, so FPGA is reprogrammable, so I can utilize the same FPGA to run many design. But in ASIC, I can only have a single particular circuit is for doing for single thing, right? So, but it is more efficient, right? So if you go this direction, your efficiency will increase. If you go this direction, your flexibility will increase. But we don't want flexibility nowadays. We need efficiency. So we are going this direction, right? So that's why this popular, this FPGA ASIC based design become that much popular in recent times. Okay, so this particular diagram again summarize the things, that if you go to a general purpose processor, so speed up is 1, but if you run the same thing in FPGA, it will be 5 or 50 times faster than a general purpose processor. And so even the performance per power, right? So the normalized performance per power or watt is almost 1100 times faster than a general purpose processor. But obviously, when you try to develop something for a, you need more time to develop, right? So if you run the GPP, general purpose processor, you just run the code, it will work. But if you go to FPGA, you need some time to develop, right? So this is again when once you go to this specific hardware accelerator, you need this software, EDA software. And as the next slide is almost already covered. obviously RTL is the de facto standard, but can I go beyond RTL? And that is where this particular course is more focused, that it actually helps developing application specific hardware or hardware accelerator, not from RTL, rather from a untimed C code. Right, here is a good example, that if you just think about a counter, right? So counter is nothing but C++, right? So counter plus plus in C. So you can write just this code, but if you want to write the RTL level Verilog code, you have to develop the what is the reset, what is the clock, what is the register width, and then every clock passage clock, whenever clock comes, you will check whether the reset is 1. Then if it is reset, then you do the reset, else you just increase and so on, right? And then finally you put that value into output, and the corresponding design in hardware is like this. But in C code, this is nothing but C++, right? C equal to C plus 1. So obviously, managing something timed or with clock is more difficult. So obviously, C is better, and that is where our course is fall into, right? So if you just to summarize in one last slide, is that high level synthesis is basically converting the C code into RTL, and here it's showing the kind of number of line of code is increasing, I mean abstraction. So from 1 million gate, you will have kind of 300k line of code in RTL, which is 40 line of code into in C. And so there is another biggest advantage is that once you run a C code, simulate, right? You have to test whether your code is correct or not. If you run a gate level design, it can only run in 100 megahertz. But if you run a RTL, it is kind of 1 kilohertz. A high level synthesis, it can actually run in 100 kilohertz, and a behavioral C code you can simulate in 1 million, right? So this is the kind of benefit in verification time. So it will reduce the verification time as well. Okay.
So, but why exactly is the verification time lower for a C-based code?
Because you are not doing clock level simulation, right? So for example, your C code is untimed and your circuit is clock level. So every clock, what is happening, you have to keep track of all this detail, right? So that's why your this clock based cycle accurate simulation of RTL is much slower than a C code. I mean C code simulation. Once you run a C code in a processor, I mean in your desktop, it is much faster because you don't take care of the cycle level or cycle simulation. The cycle level simulation is not needed, right?
Okay.
Okay. Okay, I think I have already made sense, and now we are in the domain of era of machine learning, right? So, is this course will help to do something for machine learning as well? That this course is also for is useful for the machine learning algorithms. Okay, so what is the correlation between machine learning and EDA, electronic design automation? So I have already talked about this. That this is the design automation flow. And in a design automation, three things come into picture. One is synthesis. What is the software? How you convert a C code to RTL, RTL to get level to transistor level, and so on. That is called synthesis. And obviously the verification. How do you verify that when you convert a C code into RTL, your RTL is actually functionally equivalent to the C code, and so on. And test is basically once your whole chip comes out, how do you see when test that chip is actually. These are the three terminology which is very important in the electronic design automation flow, and I try to correlate this ML with these particular three things. Okay, so there are two directions of research here. The first direction is basically learning algorithm in synthesis, right? So because I'll come into those discussion that synthesis, most of the problem is actually NP complete, or they are actually hard problems. So why don't you use machine learning algorithm to do the synthesis better, right? You make more optimized design. Obviously, there are a lot of work happening there. I'm a little bit skeptical about this application because in this particular case, the availability of data is a question, right? So we do not have 1,000 already developed design with me when I'm developing the software. So how machine learning will exactly help, I'm not very sure. So, but still, there are a lot of papers, a lot of research happening in this direction. That you use machine learning algorithm, the synthesis steps, you convert a C code to RTL, where that particular machine learning algorithm will help me to give a more optimized design. The other direction is more important, that use EDA tool to improve the execution, hardware execution of machine learning algorithms. That means you try to make more hardware accelerator for machine learning or AI application. You develop a AI or ML specific processor which will actually do good for this machine learning algorithm. And we have already many like this tensor processing unit TPU from Google. I think Facebook also have something, Microsoft has something. So there are a lot of effort in this particular domain that um, uh, develop a very application specific processor for ALMI algorithms. And here this C-based VLSI design comes into picture, because even for a ML algorithm, nobody write the Verilog code, right? Everybody write a tensor code, or you can even think about write a C code for a ML algorithm. So can I convert those tensor to Verilog? Right? That's something a very quite promising area of research, and it's I think the primary focus of EDA domain, I think, in this particular area nowadays. And that to make sense that I'll give you some instances. So I'm going to show you some conferences which is top level conference in this VLSI domain. What is the tutorial or the topic of discussion in recent days, right? So VLSI 2020 topic was designing hardware accelerator for deep learning network. So there is a keynote. So these are given by the, based on this domain, right? So they are talking about this. VLSI 2020, there is another topic is boosting AI efficiency through custom compilers and approximate computing. So again, something this EDA for AI, right? This is also EDA for AI. In date is another top conference. One of the keynote topic was industry approach developing deep learning network on FPG. Again, EDA for ASP-DAC, another good conference. Topic is machine learning in test, right? Keynote talk. ASP-DAC 2019, another talk, machine learning for reliability of IC and system. Can I utilize machine learning for improve the reliability of ICs? DAC is best conference in this domain. Tutorial in 2020, machine learning in design, digital IC design and EDA. So how we can utilize, this is the first domain, that how can I help machine learning improve the EDA tools, right? And another one is the designing application processing AI processor. Again, EDA for AI. And Microsoft accelerating silicon design with cloud and ML and AI. So I think these are all just to I copy pasted from those just to motivate you that this domain is very important in for the success of this even ML and AI. And I'm going to take some time of this course just to talk about this hardware ML and AI processors. Okay, that's all from discussion. Now I'm going to give you more on the technical side or the logistic side of this course, that how I'm going to run the course, what I'm going to cover and all. So any questions so far? Before I'm going to move to that part, which is the logistical issues. Anybody has any questions?
Sir, is there any prerequisite for the course, like some electronic?
I'll cover that. Not much. Not much. Okay. So let me. So this is what I'm going to cover in this course. I'm going to cover how this code will be converted into RTL. So what is the flow, and what are the technical detail inside? What is the algorithm to be used? What are the things? What are the optimization objectives are there? So I'm going to cover all those things. And then there are another two important things I'm going to cover is, so it's not that any C code will convert into an efficient. Can I write a hardware efficient C code? So what are the things I need to take care or consider when I'm thinking that I'm going to convert this C code into hardware? So that is another important area which I'll cover in this particular course. And then another topic I'm going to cover is, so once you think about a C code, right? So you can GCC, you can utilize your GCC compiler, and your GCC compiler has 100 of optimizations. Can I utilize those optimization for generating efficient hardware? So just to say that existing optimizations already there, can I utilize them, or so that I can do a design space exploration, right? So I just use this set of subset of compiler optimization so that I get a better hardware, right? So role of these compiler optimizations in developing a good hardware from a C code. So that I'm going to cover. And then I'll cover this hardware acceleration for machine learning and AI algorithms. And then there is another very, very important concern nowadays, the security, right? Hardware. So because of this non-trusted party in the whole flow, I'll come into them in subsequent classes. There are good chance that your chip has some hardware trojan or some malicious code or malicious portion of the code that might leak some information to somebody else, right? So a lot of effort nowadays in industry, and I think is one of the second focus in this domain after machine learning, hardware accelerator machine learning, that how can you make your design secure so that even if it goes to somebody third party, they cannot do anything to this. So that they are not able to make any changes to your design. So that is what is called making a secure design. So, and I'm going to consider some part of the classes just to discuss how can I make a secure hardware from high level synthesis. Okay. And then I'm going to cover, so I convert C to a Verilog to a completely two different thing. One is untimed thing, another is timed, and there is no cycle things. So how can you check the equivalence between these two things? Can you say that this RTL that I have generated from C is basically functional equivalent? Okay, I'm going to cover that. And also I'm going to cover the overall EDA flow. That means not only high level synthesis, but very briefly that what is logic synthesis, what is physical synthesis, and what I'm going to cover those things also briefly, but my main focus is high level synthesis. And also I'm going to talk about various optimization that are getting in the whole EDA flow, because optimization is the heart of the EDA tools and that give you the best thing. So I'm going to cover many important optimizations in this course as well. Prerequisites, I don't essentially need any prerequisite, but I will expect that you know the terms like register, clock, FSM, gates, and all those things. If you say I do not know what is clock, what is FSM, what is AND gate or gate, then it will be a problem. I don't need what is to know what is CMOS, PMOS, NMOS. No need to. I also don't know much detail. But as long as you understand this is the basic digital design, it's okay. And this course is more about application of your algorithmic knowledge in design automation, right? So I'm very frequently I'm going to map a problem to a say shortest path problem, sometime to a searching problem, sometime to a color graph coloring problem, sometime to some click partitioning problem. So knowing the graph algorithms is something is important. So specifically parts of people who are coming from electronics background, I'll request you guys to go little bit about just refresh your graph algorithm knowledge. So and the shortest path kind of thing, specifically the graph related things. That's all. Because many times I'm going to map the problem into graphs, coloring problem and so on. So it's a very nice algorithmic course. To be honest, this is although name it's basically algorithm course. Apply algorithm to make design automation. Okay. So the books I'm primarily going to follow these two books. This by Micheli, and this book pirated version is available. I cannot officially provide, but if you are facing problem to getting the soft copy, let me know. My TA will help you. But you can always buy. This is a very good book. This synthesis and optimization research. Follow this book, and also I'm going to follow this this particular book, and this book soft copy is available, so you can download from the author site. You just search with this name, you'll get the soft copy. So this is the two primary books I'm going to follow, and I'm going to follow many conference and journal papers, because many recent things like ML, AI, hardware security, there is no book. You have to follow recent research papers. I'm going to follow this and I'm going to provide them to you guys. Okay. So that's about the books. Reference, there are many other books. I'm going to follow, say, one particular chapter from there, maybe one particular section from there. I'm going to give you soft copy if needed. Okay, so if needed, I'm going to provide the Xerox copy from this, but only very sub part of will be followed from these books as well. The most important thing which you people are looking for, the grading. Unfortunately, this course is where you need to be involved. You cannot just give your mid-sem, end-sem, and go away. I want you learn in this course. I'm going to put a lot of effort to teach. I usually put, and I'm going to put, and I want you put effort. So what I'm going to do, I'm going to take 4 module examinations, each carrying 15%. So that will come into 60% weightage. I'm going to give a project which will carry 20%. It's not so difficult because I'm going to give a tutorial on the one high-level synthesis tool called Vivado HLS, and then we are going to give some project. You basically synthesize using that tool. You try to apply different kind of optimization, basically getting familiar with the EDA tools of this high-level synthesis. Okay, and it's not that much effort, I can tell you honestly. Making you familiar with the Vivado HLS tool. So because once you come out from this institute and then you go somewhere, you say I have learned high-level synthesis, but I never use a tool. That does not look good. So that project will carry 10-20%. And I want to make you to come to classes every day. So class participation will continue of 10%, which is not only your attendance, but I'm going to randomly ask questions to people, and we are going to record the data. How many questions, whether you are participating or not, whether you're attentive or you're just log in and you leave. So I'm going to follow those things. So attending the class is must. So ensure that you need to come to classes every day. So class participation is something. So some random quizzes from the discussion that I'm having, or your participations, your attendance, everything will consist of 10%. And there is another 10% now marks just to give you some recent papers. You okay. It's basically again the same group. That project will 4 to 5, and so far I have 84 students registered for this course. So I'll see what is the final number. Maybe another 2 weeks. Either I'll request you guys to group yourself, or I'll randomly. I think it's better to you find your groups yourself, because you find your like-minded friends, and then the same group will do the project. And this is very simple. This story project is nothing to worry, because I'm going to give one or two papers of recent times, specifically from this MLAI side, mostly, and then you have to read the paper and give a presentation to us. That's all. Okay, so this is what about grading. And fortunately, this is the summary of last 2 years grading. Usually people score very well because they do the course sincerely. Okay, so almost 40% student get an 9, 9 or 10. So, and overall this is the course feel. Usually people enjoy this course. Overall I get very positive feedback. I do not share all the detail, but usually I get very positive feedback about this particular elective, about me as well as the course. I'm more of concern about this. So overall the positive things are there. Okay, they are the teachers. The other teachers are Devabroto, Priyanka, Mohammad, Arshdeep, Melvin, Rupak, and Jayaprakash. So they are going to help you in your project work. They are going to help me in developing the course material, and then they are also going to help you in this the last student-led discussion. So I am going to make a mentor. One of them is a mentor for your project, so that they can help you. And they are all very familiar with these tools and all those things, so nothing to worry. So they are going to help you a lot, because they all take this course with me and they are with me for last 2 years. So you can get a lot of all of us, including me. Okay, so the last slide, that acknowledgement, that I have copied many such graphs and nice things from Professor Jason Kong and Ziru Zhang. They are actually in high level synthesis domain, so I do follow their work, and so on. So thank you. So I'm going to make this course interesting and fun, and I hope you will enjoy this course. Okay, any question?
Sir, the random question is hello.
From that day's discussion only, just to make sure that you are here, you are not sleeping, or you logging